Apart from using a known Laplace transform to solve a definite integral, we haven't yet seen any applications for the Laplace transform. We will now look at using Laplace transforms and inverse Laplace transforms to quickly solve differential equations. First of all, let's briefly look again at what the Laplace transform of the derivative is. If our function is little x of t, then the Laplace transform of this function is capital X of s. Then the Laplace transform of the derivative of little x with respect to t is simply s times Laplace transform of x minus little x at 0. And the second derivative of x with respect to t is equal to s squared times Laplace transform of x minus s times the function x itself at 0 minus the derivative of the function x at 0. So how does this help when we're trying to solve differential equations? Let's look at this example. We will solve the initial value problem dx dt is equal to 2x with initial value x of 0 is equal to 3. Now, if the left-hand side of this equation is equal to the right-hand side, then the Laplace transforms are also equal. So the Laplace transform of dx dt is equal to the Laplace transform of 2x. And now we have a different equation that we should be able to solve. Let's start with the Laplace transform of dx dt, and I've listed the formula for the derivative of the Laplace transform of the derivative of a function down here again. So this is simply going to be s times Laplace transform of little x, that was capital X of s, minus little x of 0. Note the little x's and the capital X's because they're different. This is the left-hand side, and the right-hand side is the Laplace transform of 2x. Now, the Laplace transform of 2x is 2 times the Laplace transform of x, and the Laplace transform of x is of course just capital X of s. Now, if I simplify this further, sx of s minus, what is x of 0? Well, that's given as 3. I'll put a 3 in here, and that is equal to 2x of s. Now, I have an equation in s and in x of s, which I'm going to solve for x of s, because that is the solution I'm after in the frequency domain. So how do I do this? I'll bring everything with capital X of s to the same side, in this case the left-hand side, and I will factorize. So that comes to s minus 2 times capital X of s, and everything else goes on the right-hand side. So the negative 3 becomes a 3 on the right-hand side. Now, if I then divide both sides by s minus 2, I get x of s is equal to 3 divided by s minus 2. Now, I have solved for capital X, which is for the Laplace transform of x. But that's not what we were after. We really wanted to have little x. So what I now do is I transform the capital X back into the time domain, so I get my little x. So I do this by calculating the inverse Laplace transform. Inverse Laplace transform, which gives me my little x of s. No, this is of course a little x of t. And that's the inverse Laplace transform of capital X of s. So that's the inverse Laplace transform of what we had listed down here, 3 over s minus 2. And what is that? That's quickly done. That's simply 3e to the 2t. And as it turns out, this is now the solution to the differential equation I listed up here. So just to recap, what did we do? We transformed our differential equation from the time domain in the frequency domain. We solved it in the frequency domain, And we did this because solving in the frequency domain is usually easier than in the time domain, as we've just shown here. And then, of course, we have to convert back into the time domain. So we get the solution to the initial differential equation, and not to the differential equation we had in the frequency domain. And that's it.